Good morning, sir. I'm Emrakshita from ITA. My topic is about convergence of random variables. The convergence of sequences of random variables to some limit random variables is an important concept in probability theory, and its applications to statistics and stochastic processes. The same concepts are known in more general mathematics as stochastic convergences, and they formalize the idea that a sequence of essentially random or unpredictable events can sometimes be expected to settle down into a behavior that is essentially unchanging when items for enough into the sequence are studied. The different possible notations of convergence relate to how such a behavior can be characterized. Two readily understood behaviors are that the sequences eventually takes a constant value and the values in review. Definition: random variables. A random variable x is a mapping from the sample space to the real line. Example: flip a fair coin twice. The sample space is every combination of heads and tails. Choose the random variable x to be the number of heads. Let our outcome be one head and one tail. X maps this outcome to 1. Note: the notation can be confusing. In the book, usually x denotes the map and x with a subscript declines a real number. However, this is not always the case, so you must examine the context to be sure of the meaning. And the sample space is heads and heads tail and tail head and tails tails. Sequence of random variables. Such a probability theory is concerned with large sequence of random variables. This study is sometimes known as large sample theory, limit theory, or asymptotic theory. What is a sequence of random variables? Simply a set of indexed set of random variables. We will be interested in sequence that have some interesting limiting behavior. Therefore, we can say something about them as n gets larger, x1, x2, and so on xn. Proofs of convergence of random variables. Several results will be established using the Portmanteau lemma. A sequence xn converges in distribution to x if and only if any of the following conditions are met. E of f of xn tends to E of f of x for all bounded continuous functions f. E of f of xn tends to E of f of x for all bounded elliptic function f. Lim is a PR of xn belongs to C less than or equal to PR of x belongs to C for all closed sets C. Statements about sequence of random variables. Given a sequence of random variables, most likely IID, it would be useful to be able to make statement of the form: the average of all x will be between two values with certain probability. Example: flip a fair coin n times. The average number of heads per toss will be between 4 and 6 with probability greater than or equal to 70% if we flip 84 times, where n equals to 84. Or what is the probability that the average of x is less or greater than a certain value. These kind of statements can be made with the help of the weak law of large number, in short form WLLN, and the central limit theory CLT respectively. So why not state them now? Hold your CLT, make use a few different types of convergence which must be discussed first. Types of convergence. There are two main types of convergences. Convergence in probability CIP. A sequence of random variables is said to be convergence in probability to x if the probability of it differing from x goes to 0 as n gets large. P of xn to x greater than e tends to 0, xn tends to x. Convergence in distribution CID. A sequence of random variables is said to be convergence in distribution to x if the limit of the convergence considering CDF is the CDF of x. Limit n tends to infinity f of n or fn of t equals to f of t. Xn tends to x. There is also another type called convergence in quadratic mean, which is used primarily because it is stronger than CIP or CID. It implies CIP or CID and it can be computed relatively easily. QM tends to CIP tends to CID. Example of using the WLLN. Consider flipping a coin for which the probability of heads is P. Let x denote the outcome of the single toss, either 0 or 1. Hence P equals to P of x equals to 1 equals to E of x. The first equality is a definition. The second equality is a obtained by averaging over the distribution. The fraction of heads after n tosses is equal to the sample average. Note that the x are IID, therefore the WLL can be applied. The WLL says the sample average convergence to P equals to E of x in probability. You may find yourselves wondering how many times must flip the coin such that with probability is between 4 and 6 with probability greater than or equal to 70%. The WLN tells you that it's possible to find such an n. The inequalities that Justin presented on from chapter 4 can be used to show that n equals to 84 does the trick in this case, but I will separate you the details. E of x equals to sigma xn f of x. 0 of 1 by 2 plus 1 of 1 by 2 equals to 1 by 2. Xn equals to 1 by n sigma xn. Xn tends to nu equals to E of x1. Example of using the CLT. Suppose that the number of errors per computer program has a Poisson distribution with mean 5. We get 125 programs approximately. What is the probability that the average number of errors per computer program is less than 5.5? In this case, 125 is the sample size, which we hope is large enough to make a good approximation. The approximation we are making here is that the taking the sample size, mean and variance into account, it is possible to show that the question asked is equivalent to the probability of the standard normal distribution being less than 2.5, which turns out to be approximately 0.9983. Convergence in probability. Xn p tends to x equals to belongs to e greater than 0, p of xn to x greater than e tends to 0. Convergence in distribution. Xn tends to dx equals to f of xn of x gives rise to f of x fx of x at any continuity point of fx. Convergence in quadratic mean. Xn gives to x equals to e of xn to x whole power square gives rise to 0. Properties. Xn tends to x equals to xn tends to x equals to xn tends to x. D tends to c equals to xn p tends to c. Xn is to n belongs to small n belongs to capital N. Yn is to small n belongs to capital N. Then xn p gives rise to x, yn p gives rise to y equals to xn plus yn p gives rise to x plus y. Xn qm gives rise to x, yn qm gives rise to y, xn plus yn gives rise to qm x plus y. Xn d gives rise to x, yn d gives rise to c, xn plus yn d gives rise to x plus c. Xn p gives rise to x, yn p gives rise to y belongs to xn into yn p gives rise to xy. Xn d x, yn d c gives rise to xn into yn d is c into x. Let g of be the continuous function, then xn p gives rise to x is g of xn p is g of x. Xn d gives rise to x is g of x and d gives rise to g of x. Thank you.